Today's integral is built AF. And where do we even start? Well, that's easy. We start off by calling our integral here I, so we have something to refer to. And now we can answer the question of how do we begin integrating this monster? Well, a good place to start would be a substitution where we let the inverse tangent of x equal t. Because if you differentiate this, it means that 1 by 1 plus x squared dx equals dt. So you have the right structures in place for the differential element as well. And as x approaches 0, then t, which is the inverse tangent of x, approaches 0 as well. And for x to approach positive infinity, we need t to approach pi by 2. Okay, cool. So that means our integral I in the t world transforms into an integral from 0 to pi by 2 of inverse tangent x, which is our t variable. Then we have the differential element dt. We're dividing by x. So if the inverse tangent of x equals t, then this implies that x equals tangent t. So we have tangent t times 1 plus tangent t in the denominator. Next up, what seems sensible is a partial fraction decomposition for this reciprocal of tangent t times 1 plus tangent t, and that is pretty easy to figure out. It should be 1 by the tangent of t minus 1 by the tangent of t plus 1. So yeah, that should do it. You have tangent t plus 1 minus tangent t. The tangents cancel out. You're left with 1. Okay, this is fine. This is cool. So this implies that our integral I actually decomposes into two integrals. One is that from 0 to pi by 2 of t divided by the tangent of t dt, and the other is the integral from 0 to pi by 2 of t dt divided by 1 plus the tangent of t. And the first of these integrals I have evaluated previously. Link in the description below. There's one video on evaluating this using Feynman's trick, and another using integration by parts and symmetry, which is my favorite way to evaluate this integral. That was incredibly beautiful. So this evaluates out to pi by 2 times log 2. And we're going to call the second integral here I sub 1. So how exactly do we integrate I sub 1? Well, I sub 1 here is the integral from 0 to pi by 2 of t dt divided by 1 plus the tangent of t. So a reasonable thing to do here would be to expand this tangent term. The tangent of t equals sine t divided by the cosine of t. So if I multiply upstairs and downstairs by the cosine of t, I get t times the cosine of t dt in the numerator, and in the denominator I have sine t plus the cosine of t. And now what? Well, this may not seem obvious, but we can actually evaluate this integral quite nicely using integration by parts. And I'm going to use a very intuitive approach here. I'm going to differentiate the t variable, the t function here, and that means I have to integrate, or I have to find an antiderivative for the cosine of t dt divided by sine t plus cosine t, for which I'm going to use that intuitive approach I was referring to. So, antiderivative for cosine t divided by sine t plus cosine t. In the denominator, I need a sine t plus cosine t, so that means a logarithm term should do just fine. So you have the logarithm of sine t plus the cosine of t. And what about the cosine t term here in the numerator? How do we get this one? Well, take a closer look at this logarithmic term here. If you differentiate it, then you get sine t plus cosine t in the denominator as required. But as per the chain rule, you have to differentiate the argument as well. So that means we have to differentiate sine t plus cosine t, which gives us cosine t minus sine t. So how do you get rid of this negative sine t? Well, that's easy. You just need a 1. Once you add a 1 to this term, you can expand using the sine of t plus cosine t. So you have a common denominator here, and the negative sine t and positive sine t cancel out, and you're left with twice the cosine of t. You're left with twice the cosine of t. So that means I'm going to need a factor 1/2, but anyway, that's another matter. Pause that for a minute. What we wanted here was a 1. We need a 1 here. So to get a 1, we can add t because that differentiates to 1, right? The derivative of t with respect to t is 1. And once you add the derivatives of this logarithmic term and this t function, once you add their derivatives, you get this 2 times cosine t divided by sine t plus cosine t, right? So that means to balance things out on both sides of the equation, I need a factor of 1/2. So you need half of this thing here, that is your required antiderivative. So that was the intuitive construction of an antiderivative, which I really did enjoy. That was pretty nice. So anyway, this implies that I sub 1 equals this antiderivative times the t function, so that's t by 2 times t plus the logarithm of sine t plus cosine t, where you can ditch the absolute valued signs because on this interval from 0 to pi by 2, the argument is positive or non-negative. Yeah, it's positive. Anyway, so you have this term here minus the integral from 0 to pi by 2 of the derivative of the t variable, which is 1, and you're left with just this antiderivative. That's 1/2 of t plus log sine t plus cosine t dt. Alrighty then. So what happens to this term in the limits as t approaches 0 and t approaches pi by 2? Well, as t approaches 0, you get 0 times everything, which is a 0 anyway. And as t approaches pi by 2, then you have a pi by 4 term outside because of this factor of 1/2. Then you have pi by 2 plus log sine pi by 2 is 1, and the cosine of pi by 2 is 0, so log 1, which is a 0. So you're left with pi by 2 times pi by 4, so that's pi squared by 8. Okay. Minus 1/2 of, what's the integral from 0 to pi by 2 of t with respect to t? Well, that sorts out to a t squared by 2 term, 0 to pi by 2. And these two negatives give you, the negative and the positive give you a negative sign here. So you have the integral from 0 to pi by 2 of log sine t plus cosine t dt. And this term here evaluates to, in the limit as t approaches 0, you get a 0. Pi by 2, for the pi by 2 thingy, you have a pi squared by 8. 1/2 of that, pi squared by 16, correct? Pi squared by 8 minus pi squared by 16, that's 1 minus 1/2. So yeah, 1/2 pi squared by 16 minus, wait. This factor of 1/2. So yeah, almost forgot about that. And that would have been catastrophic. So 1/2 of I sub 2. So we started off with I. We needed I sub 1, and now we defined I sub 2, and we now have to solve for this integral. Okay, the evaluation of I sub 2 was pretty fun. And once again, it required some creative thinking and an intuitive approach. So what I'm going to do here is that I can write this integral as the integral from pi by 2 of log. Notice that you have a sum of different trigonometric ratios. It would be nice if you had the logarithm of a single trigonometric ratio, preferably the cosine, because the cosine is an even function. So yeah, symmetry will help us. So how do I convert a sine t plus cosine t into something that's only a cosine structure? Well, that's easy. Notice that you can write the argument as 1 by square root 2 sine t plus 1 by square root 2 cosine t, all multiplied by square root 2. Yes, we can do that. And this is extremely cool. Why? Because the reciprocal of the square root of 2 equals the sine of pi by 4, and it also equals the cosine of pi by 4. So that means we can write I sub 2 as the integral from 0 to pi by 2 of the logarithm of square root 2 times, oh, terribly sorry about that, square root 2 times sine t times sine pi by 4 plus cosine t times cosine pi by 4. And we know that sine x times sine y plus cosine x times cosine y, all equals the cosine of x minus y. So all of this implies that we in fact have I2 being equal to the integral from 0 to pi by 2 of log square root 2 times the cosine of t minus pi by 4. And using the properties of the logarithm, we can write the logarithm of a product as the sum of individual logarithms. So we have the integral from 0 to pi by 2 of log square root 2 dt, which is pretty simple to evaluate, right? It means you have pi by 2 times log square root 2. And again, using the properties of the natural logarithm, you can write this as pi by 4 times log 2 plus the integral from 0 to pi by 2 of log cosine t minus pi by 4 dt. And I'm going to perform a substitution here where I just let t minus pi by 4 equal to u. So that means you now have the integral from, as t approaches 0, u will approach negative pi by 4, and as t approaches pi by 2, you have pi by 2 minus pi by 4, which is pi by 4. So the integral from negative to positive pi by 4 of log cosine u, and the differential element isn't bothered in terms of structure, right? And now the cosine function is an even function. That means the integrand, which is the log of your even function, the cosine function, is also an even function. So instead of integrating from negative to positive pi by 2, just integrate from 0 to pi by 4 and double the result. So finally, we have I sub 2 being equal to pi by 4 times log 2 plus twice this integral that, you guessed it, we're calling I sub 3. So we started off with one integral, as you saw in the thumbnail, and I gave you 3 more. Yeah, it just keeps getting better, doesn't it? If only the limits here would be 0 and pi by 2, I would have just referred you to a previous video where I solved these integrals. The integrals from 0 to pi by 2 of log cosine x and log sine x are both called Euler's log trig integrals, and I've solved them previously on the channel. But the problem is, this integral is not from 0 to pi by 2, it's from 0 to pi by 4, which introduces one added layer of difficulty. But there's a way around this. There's a way that we can overcome the difficulty here, and the solution development is incredibly satisfying. It is beautiful, and it involves a beautiful series expansion for log 2 times cosine x. So the logarithm of twice the cosine of x can be written as the sum over the positive integers n of negative 1 to the n plus 1 times the cosine of 2nx divided by n. This is incredibly beautiful. It's one of my favorite series expansions. And there's a link in the description below for a proof of this series expansion for log 2 cosine x. And there's also a write-up available on my Instagram. So yeah, now would be a very, very good time to like, subscribe, and share, and follow my Instagram as well, also linked in the description. Anyway, this is just beautiful. I really do love this infinite series expansion. It is incredibly beautiful. It's really elegant. On the left, you have the logarithm of a trig function, and on the right, you have this series expansion in terms of cosine. So yeah, this is pretty cool. And we need the logarithm of the cosine of x, right? So that means, using the properties of the logarithm, I can write this as log cosine x plus log 2. So just transfer this onto the right-hand side. So log cosine x equals negative log 2 plus the sum over the positive integers n of negative 1 to the n plus 1 times cosine 2nx divided by n. So using this infinite series expansion for our integral I sub 3, this implies that I sub 3 can be written as the integral from 0 to pi by 4 of negative log 2 plus the sum over n of negative 1 to the n plus 1 times cosine 2nx divided by n. And the first of these, using the linearity of the integration operator, you can write this as the sum of integrals. And the first integral here is pretty straightforward. It's negative log 2 times the integral from 0 to pi by 4 dt. Yeah, no wait, it was the u variable, but u is just a dummy variable, so let's just call it x again. Yeah, they're all just dummy variables. Call them whatever you want. You can even call them capital sigma for all I care. Anyway, so this integral here sorts out to pi by 4 times log 2, or the negative of pi by 4 times log 2 to be exact, plus switching up the integration and the summation operators gives you the sum over n of the integrals from 0 to pi by 4 of -1 to the n plus 1 divided by n, which is completely independent of the x variable with respect to which you're integrating. So we can just pop this outside the integration operator. So let me just sort this out. Okay. Out you go. And here's the integral operator. Integral from 0 to pi by 4, that is. Okay, so that means you have negative pi by 4 times log 2 plus the sum over n of -1 to the n plus 1 divided by n times the integral of cosine 2nx would be sine 2nx divided by 2n, right? And the limits are 0 and pi by 4. So we can write this as negative pi by 4 log 2 plus sum over n of -1 to the n plus 1 divided by n squared, and we have this factor of 1/2 outside, and sine of 0 is 0 anyway, so we have sine 2 times pi by 4 is pi by 2, so we have n pi by 2, which is interesting. Now if n is an even integer, then you get sine of some even multiple of pi, a sine of some integer multiple of pi, that is, and the sine of any integer multiple of pi is 0. So we need the values of n that are odd. So we only need the values of n that are of this shape, 2k plus 1, where k runs over the non-negative integers. You have to include 0 to include n equals 1. So this implies that I sub 3 can be written as negative pi by 4 times log 2 plus 1/2 of the sum over the non-negative integers k now of -1 to the n is replaced by 2k plus 1, so you have 2k plus 2, even number. -1 to the even number is just 1. And here we have the sine of some odd integer multiple of pi by 2, which is -1 to the k in this case, right? -1 to the k, yeah, that'll cover it, divided by 2k plus 1 squared. And this infinite series here is a very special constant. We recognize this as Catalan's constant. So that means we have negative pi by 4 times log 2 plus 1/2 of top g, that is Catalan's constant. Wow, now that was just incredible. And all that's left to do now is to piece together our solution developments. So we have I sub 3 and I sub 2 equals pi by 4 log 2 plus twice of I sub 3. So you have negative pi by 2 log 2 plus top g, Catalan's constant. And pi by 4 minus pi by 2 is just negative pi by 4, right? So you have negative pi by 4 plus Catalan's constant. And then I sub 1 is pi squared by 16 minus 1/2 of I sub 2. So you have a plus pi by 8 log 2. And again, you have to negate and half top g over here. Sorry about that, g. Anyway, so finally we have I, our target integral, being pi by 2 log 2 minus all of this stuff. So pi by 2 log 2 minus pi by 8 log 2. So what's pi by 2, or 1/2 minus 1/8? So 1/2 minus 1/8. So that's expanding using 4. You're left with 3/8. So you have 3 pi by 8 times log 2. Okay, nice. Minus pi squared by 16 plus 1/2 of top g, Catalan's constant. Now this was just incredible, and I really hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.